Now we want to take what we know about adding and subtracting vectors and apply it to motion. And the first thing we're going to deal with is called relative motion. And this is when we have an object that's traveling, but it has two components to its velocity. So it might be moving partly east and partly north, or partly in the horizontal and partly in the vertical direction. So the best way to look at this is to just work through an example. So suppose we have a swimmer that can swim at a speed of 1.8 meters per second. They want to cross a river that's 200 meters wide, but has a current flowing at 1.2 meters per second west. And if the swimmer goes directly north across the river, we want to find A, her velocity relative to the ground. So the first thing I'm going to do is draw myself a little diagram. So I'm going to draw the starting and end points. So this is my river. It's 200 meters wide. And the swimmer is going to start here on one side, and it's going to swim directly across, swimming at 1.8 meters per second. Now, the problem is the river itself is moving west in this direction at 1.2 meters per second. So what that means is that the swimmer will be pushed by the current and will end up swimming in this direction. So we want to find this velocity. So obviously we need to know the length of this vector and also the direction that they end up heading. So the good thing about this question is it's a nice right angle triangle because we're dealing with a swimmer pointing north and a river flowing west. So I can find the magnitude using Pythagoras. So I have 1.8 squared plus 1.2 squared. And I find that the swimmer is swimming at 2.16 meters per second. Okay, that's the magnitude when we add in the speed of the water. Now to find the direction, again, it's quite straightforward. Tangent of that angle is the opposite side over the adjacent side. So that works out to be 33.7 degrees. So the velocity of that swimmer is 2.2 meters per second. So again, I've rounded this answer to two significant figures. And they're swimming at 34 degrees. And that is the direction west of north. Okay, so it's basic vector addition. We're adding the velocity of the swimmer and the velocity of the water to get a resultant. So in part B, we're asked, how long does it take her to cross the river? So again, the river itself is 200 meters wide. And the swimmer is swimming across at 1.8 meters per second. So in that direction, 200 meters, they're traveling at 1.8 meters per second. A lot of people get confused and think that they need to use the resultant velocity. But we can't use this vector because this distance is more than 200 meters. The 200 meters is from here to here. So when you're finding that time, distance divided by velocity, the 200 meters has to be divided by the vector that's in that 200 meter direction, which is the 1.8 meters per second. So it takes the swimmer 111 seconds to cross the river. Okay, what about part C? What direction should the swimmer swim in order to land directly across? So again, we know that because the river is heading west, the swimmer will end up traveling downstream and end up somewhere west of where they want it to be. We want the swimmer to land here directly across. So in order to land directly across, the swimmer is going to have to head upstream a little bit. Let's give ourselves a new diagram. So again, here is my river. It's 200 meters wide. And this time, I want my resultant to be a vector that goes directly across the river. So I want the swimmer to swim in this direction, so that when I add in the velocity of the river, I end up traveling along this vector. Okay, so this will be their resultant velocity. By swimming in this direction, the river will push them and they will travel this way. Right? If you've watched the videos on YouTube that I had linked with the boat trying to travel across the river, or the airplanes trying to land in the crosswind, it'll make sense that by pointing in this direction upstream, you'll actually travel straight across the river. So now we want to find the angle here that they need to swim. Right? What angle upstream? So this is again the 1.2 meters per second. And this vector is the 1.8, right? This is the swimmer. The swimmer has a maximum swimming speed of 1.8. So to find that angle this time, because I have the opposite side and the hypotenuse, I need to use my sine of that angle, which is going to be opposite over hypotenuse. And that gives us a direction of 41.8 degrees. And again, that is the direction east of north. Right? So if they head at 41.8 degrees east of north, and if we round this to two significant figures, that would be 42 degrees east of north, they'll end up traveling directly across the river when you account for the river traveling west. One other thing you should be careful of is there could always be a part D to this question, which would ask you how long does it take to cross the river. The time here is going to be different because the time that it takes to travel this 200 meters is going to be longer because they are no longer traveling at 1.8 meters per second in that direction. They're traveling much less than 1.8. It will take longer to cross the river this time. So keep that in mind, that the question could always be one step further. They might ask you to find the resultant velocity and how long it takes to cross the river. Okay, try some of the questions from the textbook on relative motion, and as always, if you have any questions, you can always ask me in class.